Hi guys, today we're going to talk about the rational parent function. So we're kind of moving into a new unit, and rational again has a root word of ratio, and ratio means fraction. So when we talk about the rational parent function, the equation will be a fraction and if I put x on the top, well, then that's really not going to help me with my fraction. Let's see. Hi everyone, today we're going to discuss the rational parent function. In the last week or so, the experience that we have with rational things are rational exponents. And if you remember from that unit, when we talk about rational, the root word of rational is ratio, and a ratio can be written as a fraction. So when we talk about the rational parent function, we're talking about the parent function whose most basic form includes x, but is a fraction. So the equation would be y equals, you have a fraction bar, the x is in the denominator, and then the most basic number would be in the numerator, 1. So it's sort of like the coefficient because it could jump out in front and be out in front. You could also write this as f of x equals 1 over x, and that would be completely fine. But the equation is y equals 1 over x. That's the rational parent function from which all other rational functions come from. So my table, if I wanted to fill in my values, my table would require that I take my x value and I substitute it right down there in the denominator. So my x value would be -10, but then my y value would be 1 over -10, so -1/10. A small fraction close to 0, but that is the exact value. So every time I take my x value and I use it as the denominator of the fraction, 1 over -8 is -1/8. 1 over -6 is -1/6, and so on, until we get down to this one. Because 1 over 0 has a special situation. When x is 0, there's no way that you can divide 1 into 0 groups. It's just not possible. And so typically in class when we say, can you divide by 0? You say no, and the reason is because at that place it's undefined. So there is no point where x is 0. There's no ordered pair to put a point. So what I'd like for you to do is pause your video, continue filling in the table, and also continue writing your ordered pairs out to the side. So check your x and y values with mine, check your ordered pairs with mine. And what I want to point out is that as x increases, let's not talk about decreasing, let's talk about just as x increases, as x goes to positive infinity, almost talking about end behavior here. As x goes to positive infinity, well, y is going to go to 1 over whatever this is, so 1 over positive infinity. So I want you to think about what happens when you take 1 and you divide it by a number that just keeps growing. Think about what happens with the fraction 1/2 and 1 over, I don't know, 1,000,000. There we go. Think about what happens with those. Which one is bigger? 1,000,000 is a bigger number than 2, but when you put it in the denominator, 1/2 is bigger than 1/1,000,000th. 1/1,000,000th is very, very, very small. And as we have infinity, so as the denominators are approaching infinity, that means they're getting really, really big. And what that in turn means is that this fraction, 1 over infinity, that fraction is getting very, very small. Now, it's never going into negative numbers if my denominator is increasing, because 1 over a positive number is never going to give you a negative. So it's not turning negative, but it's getting really, really, really small as the denominator increases. So what we say is that as x goes to positive infinity, y approaches 0. It gets so small, but it never turns negative. And so what that means is that it's approaching 0. And we're going to see what that looks like whenever we get into our graph. So I want you to take a moment to plot your points, and it's going to disappear from your screen, but hopefully it's still on your paper. When you graph -10, -1/10, that's really close to the x-axis. -1/10 is only 1/10 down from the x-axis. So you're going to have really close points to the x-axis, but they are going to get further away. So -8, -1/8, -6, -1/6, -4, -1/4, so that's kind of like -0.25, -2, -1/2, so that's right in the middle. If I had -1 and I put 1 over -1, I would have this point right here, -1, -1. And then when I graph where x equals 0, all of a sudden I have something that's undefined. So it kind of looks like it's leading this way, but then it drops. And then I pick up where x is 1. So 1 over 1 is here, is 1. 1 over 2 is 1/2. 1 over 4 is 1/4. 1 over 6 is 1/6. And 1/8 and 1/10. So it kind of looks a little strange. If you were to connect this, you would connect here, and then you wouldn't jump up here, because if you jumped up here, then that means that there would be some point where x equals 0. Some point where my graph crossed the y-axis and it had a point where x equals 0. And that doesn't happen because when x is 0, my graph is undefined. So I can't have any point where x is 0. I can't cross the y-axis at all. So what it looks like is this. And it picks back up. And it curves. And it goes like this. This is what the graph of the rational parent function looks like. And if you look very closely, the arrow goes really far, but it's not supposed to touch. The arrow goes really far this way, but it's not supposed to touch. So what is there along the y-axis? What is that called when part of the graph approaches and gets very close and closer, but it never touches? It's called an asymptote. So we have an asymptote along the y-axis. We also have an asymptote along the x-axis, because this part of the graph is approaching, but it's not ever supposed to touch. Now, if you look closely, your pen or your ink on the screen probably bled onto the line, and so it might look like it's touching, but in reality, it's not. It's still 1/10 of a distance away, and 1/11 a distance away, and 1/12 a distance away, so it's never actually touching. There's an asymptote there. So for the key attributes, the graph has a name. So we've talked about parabolas, we've talked about cubics, we've talked about linear functions. So a lot of these have names, but this graph is called a hyperbola. A hyperbola, almost like a parabola, but a hyperbola. The prefix hyper means like more, increased. So this is a hyperbola. That's the name of this shape of graph where it looks like this. It's a hyperbola. Now let's talk about the domain and the range. Domain, range. By now, hopefully, with your practice of domain and range in Algebra 1 and in Algebra 2, hopefully you remember that for domain and range you need to try and find boundaries. The domain from the left to the right would be a boundary on the left side, which I don't have because there's an arrow, and a boundary on the right side, which again I don't have because there's an arrow. So if it extends from negative infinity to the left to positive infinity on the right, what is that called? Well, that's called all real numbers. With the range, I need to find the boundaries on the bottom and the top. So a boundary on the bottom would be here, but there isn't one because we have an arrow going to negative infinity. And a boundary on the top, again, there is not one because there's an arrow going to positive infinity. So if your range goes from negative infinity to positive infinity, what is that called? That's called all real numbers. Now we do need to talk about the exception. The exception is the asymptotes. So when I'm discussing the domain is all the x values that get used, all of them, all of them, all of them, but then all of a sudden, boom, we hit here. And there is an asymptote right here. And it extends. And that asymptote is at x equals 0. That means that the graph never touches the x value of 0. So my domain is all real numbers. However, my domain is all real numbers except x cannot be 0. But it's everything else. So my domain is all real numbers except x cannot equal 0. That is part of the domain. You must include this. Because if you only say all real numbers, that means that the domain includes 0. And it should not, because there's an asymptote there. Same situation with the range. The range is all of the y values that are getting used. So everything from negative infinity all the way up, 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 up until you hit right here. There's an asymptote at the line y equals 0. Meaning the graph will never touch y equals 0. There will never be a point that has 0 for y. So my range is all of real numbers except y cannot equal 0 because there is an asymptote there. So I'm going to go ahead and put that in my notes. Because of the asymptotes. Because of the asymptotes. You have to take those out of the domain and the range. Now, there's an interesting consequence when the domain and range are all real numbers except x and y can't be 0. So let's talk about the x-intercepts and the y-intercepts. So when I look at my graph, along the x-axis, there's an asymptote. So there's no point where the graph is going to touch the x-axis. So are there any x-intercepts? No, there are none. For the y-intercepts, are there any points that are going to be on the y-axis? No, because there's an asymptote there. So there are none. We do need to mention where those vertical and horizontal asymptotes are. So there is a vertical asymptote. And that vertical asymptote is right here. Vertical means up and down. That's happening where the x values are all 0. There's also the horizontal asymptote. That horizontal asymptote is happening here, side to side. And that's happening where all the y values are 0. Now it's interesting to note, and it should be noted, that the vertical asymptote, y equals 0, shows up right here as being taken out of the domain. And the horizontal asymptote, I think I said y equals 0, I meant x equals 0. The horizontal asymptote of y equals 0 shows up right here as being taken out of the range. So these should match. If you have asymptotes, then those numbers where the equations are, they should be taken out of the domain and the range. So keep that in mind. And then the last thing that we want to discuss is the end behavior, and we already talked about it a little bit, but not a lot. So end behavior. Let's first talk about as x goes to negative infinity, y goes to what? So we're going to look at our x values. Here's my x-axis. As x goes to negative infinity, going that way, what's the graph doing? What y value is the graph approaching? What's approaching this asymptote, right? This asymptote is happening where y is 0. So as x goes to negative infinity, y is going to 0. As x goes to positive infinity, so to the right, let's talk about where y goes. So in the graph, as x goes to positive infinity this way, the graph is coming down, 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 and then it's kind of flattening out. And it's never going past the asymptote, which is at y equals 0. So again, it's approaching 0. That's where it starts to flatten out. And remember, we talked about that up here. As x values get bigger, the y values get really, really, really small, but never negative, so they approach 0. As x goes to negative infinity, as x goes to positive infinity, 1 over big numbers, getting bigger and bigger, this whole thing will go to 0. So those are my end behaviors, and this is the rational parent function. After this, we're going to talk about other kinds of rational functions in the unit. And we're going to include some polynomials from the last unit.